Hello guys, in this lecture we are going to learn about semiconductor junction diode under the topic of semiconducting materials. Most semiconductor devices contain at least one junction between the p-type and n-type material. The p-n junctions are fundamental to performance of such as rectification, amplification, switching, and other operation in electronic circuits. The junction fabrication is a broad subject. The basic method for forming p-n junctions are growth junctions, alloy junctions, and diffuser junctions. The type of junction we seek is a change from n-type to p-type material in a single crystal. Therefore, we may change the dopant from donor to acceptor during the growth of crystal. Alternatively, we may introduce impurities of one type into regions of a crystal which was grown with the lighter doping of opposite type. In either case, only the doping is changed at the junction. There are no gross changes in the lattice structure itself. Let's see the junctions one by one. First is growth junction. A method of junction fabrication that was popular in earlier days of semiconductor devices. That development is growth junction technique. In this method, the dopant is abruptly changed in the melt during the process of crystal growth. This figure A shows a growth junction where this is n-type material and p-type material. With the help of these two materials, centrally it is generating a junction which is called as growth junction. The original growth junction technique has been supplanted by the more flexible methods of introducing the junction into the crystals after growth. An important exception, however, it is epitaxial growth of p-n junction, which is used widely in integrated circuits and for other applications. An epitaxial layer of one type can be grown on a substrate of opposite type to form the sharp and single crystal junction. Epitaxial growth technique is one of the most important and versatile method of crystal growth for device application. It is growth of a thin crystal layer on a wafer of compatible crystal. The substrate crystal may be a wafer of the same material as grown layer or a different material with a similar lattice structure. In this process, the substrate serves as the seed crystal onto which new crystalline material grows. The growing crystal layer maintains the crystal structure and the orientation of the substrate. The technique of growing an oriented single crystal layer on the substrate wafer is called epitaxial growth or epitaxy. A variety of methods are used to provide the appropriate atoms to the surface of growing layer. These methods include chemical vapor deposition, liquid phase epitaxy, and molecular beam epitaxy. These methods are widely used in integrated circuits and for other applications. Next junction is nothing but alloy junction. It is also called as fused junction. This is a technique for making PN junction by alloying of a metal containing doping atoms on a semiconductor with the opposite type of dopant. The second figure shows the fused junction, or it is also called as alloy junction. The fused junction diode is prepared by placing small sphere or dot of indium on a wafer of n-type silicon. As shown in here figure, you can see one dot is appeared, which is called as indium on n-type or silicon material. N-type material, or it is of silicon material. When this combination is inserted in an oven for several minutes at a temperature that is suitable high temperature, the indium fuses to the surface of the silicon and produces p-type silicon immediately below the surface. Thus, an PN junction is formed between this P region and the main body of the N-type silicon wafer. And the next one is diffused junction. Impurity diffusion is another most common technique for forming the PN junctions. This method, along with the use of selecting masking to control the junction geometry, and made possible the development of integrated circuits. In a special furnace at about 1000 degrees Celsius, the impurity atoms are diffused on a wafer of particular type. A PN junction can be obtained. By selective diffusion, it is possible to have many isolated PN junctions on a single wafer. Let's see the ion implantation. A careful alternative to high temperature diffusion is the direct implementation of energetic ions into the semiconductor. The process can be done at low temperature in an ion implanter. It is possible to implant impurities which do not diffuse conveniently into the semiconductors. In junction diodes, the important rectifying action takes place at the boundary between the p-type and n-type materials. The area of this boundary is usually much greater than it is a transverse depth of transition region. Thus, the analysis problem is essentially one-dimensional, the important dimension being transverse to the boundary. This figure shows a schematic sketch of PN material itself, in which a circled charges represents the immobile ionized acceptor and donor ions. In this figure A, some of the here circles are shown, which may be a fixed electrons or fixed holes. This circular shaped charges shows it has immobility, means fixed electron and fixed holes. And this with the sign showing negative charge and positive charge. These are electrons and holes with the mobility. Figure B is shown, figure B here is shown the concentration of immobile ions in the vicinity of the junction. You can see here, this is a P region, N region, and this is a P region, and this is a junction. You can see the concentration of donor on N region is very high, as in the junction it is going to decrease. Again here on right hand side, P region side, the concentration of acceptor is very high, as the junction at the junction it is going to decrease, and another side it is going to nullify. The exact nature of the transition from donor to acceptor differs between the growth junction and the fused junction, being much more abrupt in the case of fused junctions. However, it is having a essential behavior much same in both the cases. Means in case of growth junction as well as in the case of fused junction. Under the equilibrium condition, when no external voltage is applied to the PN junction, there is a dearth of holes and free electrons in the vicinity of the junction. In this figure C, you can see here, suppose that voltage or the electric field is not applied to the PN junction, across the PN junction, then the concentration of electrons on the N region is very high, and on P region the number of holes or the concentration of holes are very high. And in the PN junction, at the PN junction, both the concentrations are very negligible. You cannot say it is not any not having any holes or electrons, but you have to say that here you can say at junction there is concentration of electrons holes is very less. This leaves the immobile ion in the region unneutralized. The positive and the negative ions on the opposite sides of the junction that are uncovered and produce an electric field across the junction. If you are looking for figure A and figure D, consider that a voltage is applied across the PN junction. Then this junction appeared, and the mobile charges will move towards as the law of attraction. And as per this, the figure D shows that as compared to figure C, it changes their barrier, that called as the barrier charges. You can see here on the N region side, it appears with the positive, and on P region side, it appears with the negative. And junction, whatever the barrier was here, as you can see in the figure, C, as compared to this, in the figure D, this barrier is going to decrease. The barrier field, as it is termed, and it is a result of unstable saturation initiated by the fact that when the electron and holes in the junction are combined, the resulting uncovered ion produce a field that drives the remaining electrons and holes away from the junction, which in turn uncover more ions. The entire transition is shown in the here figure D, which takes place within a space of a small fraction of millimeter. What about the energy? During this process, the energy levels is shown in figure E. The energy required to move an electron from N region towards P region varies with the position. As you can see, as electrons moving towards the holes, the energy required is going to increase, and it requires the energy to move from N region to P region. Transfer of electron transfer of electron all the way across the junction requires the expenditure of energy, which is in electron volt, and thus termed as barrier energy. That is called as barrier energy. An equal amount of energy is involved when a hole is moved from the P region to N region. The energy, that is barrier energy, is a function of the thickness of uncovered region, and greater the thickness, greater the energy required. Now let's see the current flow across the biased junction. If the P material based is biased positively with respect to an N material, as you can see in the figure, in this figure, P is having the holes that is positively charged with respect to N, and N is of negatively charged, having a negative charges. Then the bias potential exerts a force on the holes. As you can see in this figure, a battery is connected across the PN junction. So there are mobile charges as a hole and electrons, and getting the energy from this battery to move from P junction to N junction or N junction to P junctions. And this bias potential exert a force on hole and free electrons in P and N material respectively. The opposes the resulting force of barrier field and causes these carriers to crowd closer to the junction. Obviously, the holes attracted towards the negative charges and negative charges attracting to the positive charges. That's why whatever we looking here, you can see the positive terminal of the battery is connected to the P region, and negative terminal of the battery is connected to the N region, so that this positive charges going to attract towards the negative terminal of the battery. So this dotted line shows that barrier and all the charges are crowded at this junction. So this barrier is very less here. As compared to this, we can see to the another figure here. As compared to above figure, you can see here a negative terminal of the battery is connected to the positive holes and P region, and positive terminal of the battery is connected to the N region. As law of force of attraction, the positive charged holes attracting towards the negative terminal of the battery, and uh, negative charges going to attract towards the here positive terminal of the battery. So that's why the barrier between the at the junction is very high as compared to the first case. For a given temperature, more of the majority carriers can now surmount this barrier energy than the higher barrier. At the same time, the number of intrinsic carriers that conduct the electricity in the opposite direction is unchanged because the rate at which the intrinsic carriers are produced is determined by the breaking of covalent bonds, and it is not affected by the externally applied voltage. A large current thus flows, and applied voltage of this type is called forward biased. This first case, whatever we see in here, this is called as forward biased. And application of a voltage of the opposite polarity, negative polarity to the negative polarity of battery to P side, and positive polarity of battery to N side. This termed as reverse bias. The second case we seen just now, that called as reverse bias. The overall current voltage curve is shown in the figure also here. The figure A shows that there is no biasing, and figure B shows with the forward bias, and figure C shows reverse bias. As noted earlier, the small current in the reverse bias mode is due to the thermally generated minority carriers, which are always present in each region, and which of the cores make transfers across the junction region. At higher voltage in the reverse bias, breakdown sets in. Suppose that voltage is very high applied in the reverse bias mode, and with the very high voltage, then that junction may be break, that nothing but breakdown sets in. Germanium diodes require much less forward bias to conduct. This can be of advantage in low voltage circuits. Germanium diodes have low resistance for forward current, and germanium is a better conductor than silicon. However, the silicon diode is still superior for more application because of its low cost and lower leakage current at higher temperature. Silicon is mostly used these days. Now, as we seen the current flows in reverse bias and forward biases, this curve shows the current voltage curve of PN junction. With the examining this figure A and this figure D, which shows that on opposite side of the PN junction, there are regions containing immobile charges of opposite sign in close proximity to each other. This is the situation that exists in any capacitor. Means you can see here in the forward bias condition. Suppose this is nothing but the barrier or the junction. At this junction, the holes on the P side, the holes are crowded here, and negative charges will be crowded here at this condition, and the same condition appearing in the form of capacitor. Since the capacitance of capacitor depends on the spacing of charges, and it is greater if the charges are closer together, the capacitance of PN junction will change with the applied voltage. it diminishes with increased voltage in the reverse bias direction. As you are going to increase the voltage, then the barrier between that two regions is going to decrease. As the voltage decreases, the barrier is going to increase between them. There are many diode types and applications in the electronic circuits. As you can see in this figure here, few of the structures are showing here are devices. This figure shows a various notation for a PN junction diode. The P type and N type portion of the diode are called anode and cathode, which is shown here. P side is called as anode and N side is called as cathode. Here also you can see anode, cathode. Here also anode, cathode, anode, cathode, anode, cathode, like that. The direction in which the diode resistance is small is shown by the arrowhead. And it is also direction of conventional current flow when the diode is forward biased. There are few very important applications of PN diodes which depends on how diode is biased. The 6 important diode types are nothing but the rectifying diode. Next is the light emitting diode, then the laser diode, Zener diode, photodetector, and solar cell. Let's see the rectification. This curve shows the current voltage curve, and it is the characteristics of the diode. And it is easy to see how rectification can obtain by such a device. With the alternating current imposed across the device, the applied voltage varies sinusoidally from reverse to forward bias. In the reverse mode, no current passes. In the forward mode, there is no barrier to current flow. A half-wave rectification results the diode is said to have low impedance in forward bias, high impedance in reverse bias. This is about the semiconductor junction diodes. Thank you for listening to me. Thank you very much.